to Abhishek Naik, who's going to present from University of Alberta. Go ahead and take it away, Abhishek.
All right, do you see my screen? Okay,
Yep.
great. All right, welcome everyone. Thank you so much for taking the time for all around the world to have a discussion about personalized brain state targeting via reinforcement learning. So this is joint work done with Amritpal Singh, Kaushani Biswas, Harini Sudha, Matthew Schlegel, and Kyle Matheson. All right. So the motivation for this research project was that to do something to help achieve desired states of the mind without active effort by an individual. So let me make this motivate this with an example. So there's something from my personal life that I have been trying to meditate recently, as many of us might have tried. And so I haven't been particularly successful with it in the sense that, so there's this voice. So there are many ways to do that, right? And there are some apps, and uh, so there's this voice that tells you that, okay, close your eyes, take some deep breaths, like hold it for a few seconds, release it, count your breaths, or focus on some part of your body and relax it, and things like that. And so I keep getting distracted by other things that are going on in my mind. And so I was wondering that, hey, so when I watch some sports on TV, I'm instantly excited, right? So like something is going on, I'm super enthusiastic, focused on that. Wouldn't it be nice if there was something like that? So let's say look at a screen, and in like 2 minutes it takes me to a meditative state, right? Wouldn't that be nice? And so that was the motivation behind this research project, and I was wondering how we could do that if possible, right? So maybe meditative state is one example, but you can stretch it to think that you could, go to, for example, a deep sleep state, right? So imagine that you just had a surgery of some kind, you're in an accident or something, and now the surgery was successful, and now you're in the recovery room. But unfortunately, you're drugged, and you have a lot of physical discomfort, some pain, and all of these things can throw off a person's sleep schedule, right? And all the noise and lights in the recovery room don't really help. So it would be nice if there was something that you could just look at that would instantly, take you to the deep sleep state. And so maybe it happens over a period of 2 minutes or 5 minutes, but it would be nice if it was something you didn't have to actively uh, try to do, right? And so yeah, so some other people have also thought about how they could potentially make this happen. And so there are these, so if you take sleep as an example, there are these sleep assistant systems. So the simplest one could be something open loop, which is like you play lullabies or some soothing music and hope that it puts you to sleep. And I call it open loop because there is no feedback mechanism here. So maybe you are not falling asleep, and yeah, it keeps on playing and doesn't really help you, or you've fallen asleep and it's actually creating some noise that might wake you up, right? So there's no feedback mechanism here. And so that's why I call it open loop. In contrast, there are these closed loop approaches. So for example, Zhang et al. In 2015 came up with something called iSleep, in which uh, it monitors your EEG data in real time, and based on some hard-coded thresholds, it decides when a person would have fallen asleep. And again, based on some other thresholds, tries to decide which sounds to play in order to put you to sleep, right? And now there are some more proprietary companies that are trying to do something in this space: Muse, Mind Alive, Snozic. Um, I'll get into some of the issues there, which we are trying to solve. But all of this relies on the existence of a goal state that the system can take you to, right? So, for example, in sleep, there is this deep sleep state that the objective of the system is to take you to, right? And so, fortunately, at least in sleep, there is some evidence um, that your alpha levels go down and your theta levels go up, and that is an indication of an onset of sleep. So maybe there is something that we could work with there. And now, if there are these goal states, we also need to identify them, right? And so you can imagine there's a system which takes your EEG data in real time, for instance, and is able to give a score to every at every second. For say that, okay, you're this state, you are like 0.6 or 60% close to a deep sleep state, right? Versus like a state which is like 98% close. It would be nice if this was measurable, quantifiable, um, so that you can actually mediate the audio or visual cues that you're using to get to this particular goal state, right? And so fortunately, there is some recent research which uses some recent deep machine learning techniques trained on data sets collected from a large number of people all over the world to categorize these stages. Okay, that is something maybe we can use as well. And then finally, we also need to actually be able to affect the brain state, right? That if I play some sound, that should actually uh, help you get from state A to state B without you doing something about it. And again, there is some research which says that in case of sleep, there are some audio cues like binaural beats or some kind of pulses that they can give of certain frequencies that induce a certain type of response in the brain. Okay, so these are all the ingredients that you could use. Um, and the closed loop systems that I talked about earlier try to use some or more of these techniques, but they are limited in a sense because they're trained offline from data collected from a population, which is not tailored to any specific individual, right? And if any offline adaptation per individual, if at all, is very slow. And if you're using some kind of this brain-computer interface, it is critical to have the speed of adaptation to be quite high because poor initial performance or long training periods are barriers to adaptation of such technologies, right? So if I put on the system and it is making these weird noises and for 20 days it is not really helping me sleep, I'm not going to use it. So we need something which acts in real time, is able to learn from the data it collects from you online and react to it and learn very quickly, right? And so that's where I think reinforcement learning comes in. So what is reinforcement learning? So it's like it's a it's a subset of machine learning in which the system learns via interaction with the world. So for example, this is the agent which is acting, and it is interacting with the world. It observes, it gets this set of observations from the world, and in response to those observations, it performs some actions, right? And for that action, it will receive another observation from the world and a corresponding reward, right? And so to make this a concrete, so imagine that you're learning to ride a bike, right? So um, so yeah, so you are trying out different things. So you're on the bike, you're trying to balance, you're trying to pedal ahead, and there is no one like your parents are there to like help you, but they can't really tell you that, you know, apply 40 pounds of pressure on your right foot while leaning 3 degrees to the right, right? Like they can't give you such instructive feedback, which is common in the supervised learning setting, right? That for every instance, you have some particular label associated or a correct action associated with it. You don't have that. But what you do is you try something and maybe you fall and you're like, okay, maybe this was not a good thing to do. You get like a negative reward. And so now you try a second thing and maybe that works and you're able to cycle ahead and your parents are clapping, and that's the positive reward that you're using to reinforce that action, right? And so that's basically what the reinforcement learning paradigm is. And so what we're trying to do is, uh, let's say the world is this person who's using this particular system. So you get some real-time EEG data from the world, and then you provide some audio-visual cues to to this person. And then the reward is your distance to the goal state, which you can measure in some particular ways. And so, yeah, so we developed a proof of concept system in which we made a lot of simplifying assumptions. And uh, so basically, model the entire brain state as this scalar, which lies between 0 to 1. And the current state is like one particular real value between this thing. And the goal state is, let's say, somewhere here, right? And your actions is to these three, that the effect of this action is that this current state moves towards the right, or it increases, move towards the left, or stays there. And we made a model of how the brain state, the simplified brain state, could change. So it's drawn from a Gaussian and has some effect of the action. And so this keeps changing, and you take some actions, it changes, and you get some reward proportional to that. And so based on a recently proposed algorithm, so when you start training, this is the goal state. This is how the state of the brain is evolving. And you're trying out different actions. They don't really seem to work. And this action says that, okay, the arrow means that it takes the brain state towards the right or the left. And towards the end of training, you'll see that it has learned that wherever the brain state is, if it's on the left of the goal state, take it to the right by taking this right action, or take it to the left using this left action if it's here, right? And so after a few interactions with the real world, this system learns this policy very quickly. And that is something very encouraging that we have. And so now, to moving on from this prototype to product, there are multiple things that we are doing. So like the obvious one is take the full multidimensional, let's say 30-dimensional vector of EEG data as input, along with certain features that can help out, like time of day, age of the individual. And then you categorize the input that you see, this entire thing, based on how close it is to the goal state that you have, which is the sleep state. And then actually use full-fledged audio and visual cues to affect the brain state instead of the simplified actions which deterministically affect the brain state. And yeah, so the goal is to develop an active closed loop system that learns in real time the set of audiovisual cues best suited for every individual to lead them to a physiologically objective goal state from any state. And yeah, so that is kind of it. And if you have any questions, feel free to post them in the chat here, or yeah. Thank you so much for listening.
Thank you so much, Abhishek. So just to stay on schedule so that people